In this last little section for this week, I want to discuss a couple of things relatively briefly. First one is Maxwell's stress tensor. And you'll see why I discuss that just when I start talking about momentum. Okay, what's this about? The first thing I'd like to say is that this is a little bit out of the main stream of the course, so this is a slightly more advanced thing. I will not put questions on the final exam about Maxwell's stress tensor directly, but it's still something that I think you should be familiar with, because if you carry on in physics, you might very well come across, come against it later on. So anyway, it's relatively straightforward, a bit of derivation, but it shouldn't take us too long to do that. So what are we going to do? We're going to look at the total electromagnetic force on a set of charges in a volume V. Okay, so what would that be? Let's just call that F. That would be the integral over your volume of just what's given by the Lorentz force law. So we're going to have the electric field plus speed cross magnetic field rho d tau. Okay, and I'll just rescale this. Okay, so so I can rewrite that in terms of force per unit volume if you want, where the force per unit volume, I just bring back the rho in here, and I re-identify V times rho as the current density that I have. Okay, so what is this? This becomes just rho times E plus the current density that we had cross B. So we're doing exactly the same thing that we did in the previous video, if you want. Okay, so the force per unit volume, I'll write as little f. So this is just by definition rho times E plus J crossed into B. Okay. Now what we're going to do is we're going to substitute for J using Ampere Maxwell. Okay, so what that tells us is that F is going to be epsilon 0, and I'm going to substitute also for rho from Gauss. So from Gauss. Okay, so what I get really is that rho is just divergence of E times epsilon 0. So I have this, and I'll write little parentheses so we don't get too confused. And now substituting for the current here, I will get 1 over mu 0 with the curl of B minus epsilon 0 dE dt. Okay, big parentheses in front of that, or curly brackets, all of that crossed with B. Okay, now we can use a number of little identities for this. So first of all, let's see here, you see I have a derivative of the electric field with respect to time crossed into B. But I can write this using just, you know, as if I was doing an integral by parts. This is like the d dt of E cross B. But now I have to subtract the extra term that I would generate, which is just E crossed into dB dt. Okay, now we can substitute for dB dt using Faraday. Okay, so what I get is that this whole thing is just d dt of E cross B. Should put my vector notations like this. Okay, plus E cross the curl of E. Okay, like this. Okay. So if we put things together, if I just substitute this expression here for this one here, I can rewrite the force per unit volume as being, so I've got epsilon 0 with the div of E times E, minus then the term coming from here, right? That just originates from here. E crossed into like this. Okay, so here, if you want, there's a big factorization of the epsilon 0 in front of those, and then I get the other terms. I've got a remaining 1 over mu 0, and here I can you see, just reorder the things here. I've got curl of B, curl into B, but I can use the cyclic property to rewrite this as B cross curl of B. Okay, and then finally I have the epsilon 0 d dt of my E cross B. Okay, so this is a bit of an ugly form, but actually we can notice a kind of symmetry between electric and magnetic fields. So the only point is, I mean, this term corresponds to this one here. Of course, this one has no correspondence, but if I wanted to, I could add a term corresponding to this one for the magnetic field, because we know that the div of B is equal to 0 always. So we can kind of symmetrize this to the following form. I can, you know, I could have F is equal to epsilon 0, and then the same thing that I have here, div E times E minus E cross curl of E. Okay, and then I would do plus 1 over mu 0 with, now I would do div of B, which is 0, so I can add it, times B. I'm multiplying by 0, it's still 0, minus B cross curl of B. Okay, and of course again minus my other remaining term, epsilon 0 d dt of E cross B. Right, so that already looks a little bit more symmetrical, but we can also use a little product rule. So there's an identity which in Griffiths is called the product rule 4. That you can look at, but you can just immediately apply it. It's an identity for two vector fields A, B, but you just put both of those to the electric field. And what that tells you is that the gradient of E squared is going to be E dotted into the gradient applied on E plus E cross curl of E. Okay, and of course I could do exactly the same with the magnetic field, and that simply tells us that the expression E crossed into the curl of E can be rewritten as 1/2 the gradient of E squared minus E dotted into grad acting on E. Okay. So finally, what we can get is that the force per unit volume is going to be epsilon 0. Now I'm just going to use this identity here to rewrite this one here, but I will actually extract this term out if you want and keep only this one. You'll see it's going to look quite symmetrical. So first of all, I had this term here, so div E times E, but then I have this term here coming in, plus E dotted into grad, acting on E. Okay, and again the epsilon 0 just is factorized in this whole thing. Then I have the same thing but with the B field. So very similar expression, div B acting on B, plus B dotted into div acting on B. Okay, and now I'm going to write these terms here, minus 1/2 the gradient of the bit coming from the electric field and the bit coming from the magnetic field. But this you'll recognize because it's the earlier electromagnetic energy density per unit volume, whose gradient I find in this expression here. Then I've got the minus epsilon 0 d dt of E cross B. And you'll remember our good old friend pointing at this stage here that we'll substitute for this. Okay. So a much more transparent way of writing this identity is obtained if we use an object called the Maxwell stress tensor. Okay, and this is defined as follows. So it's a tensor, it's got two indices, ij taking values x, y, z if you want. So by definition it's the following object, there's an epsilon 0, and now for the electric part, you take component-wise the electric field, EI, EJ, but with a Kronecker delta, if the two indices are equal, you subtract the whole of E squared. Okay? And then the same thing for the magnetic field part. BI, BJ, minus 1/2 delta IJ, B squared. All right. So what's the idea here? If you just look at all the indices in these equations here, and you identify with the object that you have here, you can rewrite that F is simply the gradient applied to this tensor, okay, minus epsilon 0 mu 0 with the time derivative of the pointing vector. Okay? So to get the total force, we just integrate, and what we get simply is that the total force is equal to the, if I just use the divergence theorem on this one here, I do the volume integral but apply the divergence theorem immediately, got T dotted into dA minus epsilon 0 mu 0 and the time derivative of the integral over the volume of the pointing vector d tau. Okay, so that's the rule. That's the rule for the total force that I have on charges in the volume. Okay, so you see we've found a very, very condensed expression for this this force here. Now let me just show you why this is interesting and how it kind of relates to something that we saw earlier today. Let's now consider conservation of momentum. You'll see the link in a minute. So what do I want to have? My good old friend Newton gave us his second law that tells us that the force that we have on something is related to the time derivative of the mechanical momentum of an object. Okay? What we have is that this force here, I've just written it up here, right? So it's this thing, it's this integral over the surface, the Maxwell stress tensor dotted into the surface element, but then also with the volume integral of the pointing vector, whose time derivative I'm going to take. Okay, so if you want the, well, maybe I should, I don't know if I should rewrite it. I don't think I need to rewrite it very much. The idea is that we can give interpretations to these two terms here that I would get. So this is equal to this. But what's the interpretation of these two things? So the one here is the quantity, the momentum per unit time, which flows through the surface. No, actually, this first term here is the momentum per unit time that flows through the surface of my system. That's the one with the surface integral. The second one here is essentially the momentum which is stored in the electromagnetic fields inside the volume. Okay, so essentially it smells like a conservation law. Yeah. So first of all, what we're going to do is define the momentum density in the electromagnetic fields. Okay, as the density that is here, and by convention, so of course, because it's a density of momentum, it's going to be a vector, right? It's going to be a momentum per unit volume, and by definition, this is just going to be taken to be epsilon 0 mu 0 times the pointing vector, okay, which you can of course just rewrite as epsilon 0 E cross B. Okay, now more interestingly, so if the total force vanishes, okay, so if you've got no external force acting on your system there has to be a preservation of the momentum. So what we get is that I should put this expression here to 0, but the way I can rewrite this, you see, so this one is really just the time derivative. Well, maybe we will write it fully first. Let me just rewrite everything in terms of some volume integral. Okay, because you see, so I would have the divergence acting on this. So I would have an integral over the volume of the divergence of t. Okay, and from this term here, I already have the thing, but now I can just identify my g here. Okay, so I would just get minus d dt of the integral over my volume of g times d tau. And if this is true for any volume v, that tells me that I have a conservation law. Here I could take the partial time derivative here inside. I would just get that the partial time derivative with respect to time of g minus the divergence of the Maxwell stress tensor is equal to 0. Okay, so this is the continuity equation for momentum. Okay, so, and you remember what we had before. So we had our continuity equation actually in a different notebook. So we had the continuity equation for charge, then we had the continuity equation also for the energy density. This is an equation precisely of the same form. The time derivative of some local density is compensated by the divergence of some current, therefore ensuring that the integral over all space of this density here remains constant. So that's just another example of a conservation law that you would have in there. You see, we've got charge, energy, momentum. You could play the same game with the angular momentum. So what's the angular momentum? The angular momentum, L, is really just the distance crossed into the momentum, right? So you can just write this as epsilon 0 r cross E cross B. Okay, and again, one could write a conservation law for this in the absence of external torques. You would have a continuity equation for angular momentum. But I'm not going to press this issue because it's a little bit outside of the main thing. I just wanted to go through these things because, once again, I think these objects, in particular the Maxwell stress tensor, is something that you might bump into later on in life.